In this video, I'm going to explain the classification diagram for fixed points in linear stability analysis in the plane. This is on page 138 of the Strogatz textbook, and what you can see is this plane with delta on one axis and tau on another axis, and then various parts of it are labeled. I'm going to explain what these different regions are and what the tau and delta means, and so on. Okay, so this is linear stability analysis. So first, we need to recall the usual technique for solving for eigenvalues of a 2 by 2 real matrix. Okay, so suppose that you have A equals A, B, C, D, like this. Now, in general, you can start with an abstract eigenvalue equation like this and rewrite it like this, and then we can stick in an identity matrix here and pull the V out like this. So A minus lambda I in a group times V equals 0. Now, if you'll recall, in order for lambda to count as an eigenvector, right? So for lambda to count as an eigenvalue, you need for there to be a non-zero V that solves these equations. And the key to making that work is to look at this last one, because A minus lambda I is also a square matrix. And for there to be a non-zero solution to a square matrix times a vector equals 0, the square matrix must be singular. So A minus lambda I must be singular for there to be such a V. If A minus lambda I is not singular, then the only solution to this equation would be V equals 0. Okay, well, if you'll remember, there's a long list of conditions for a matrix to be singular that are all equivalent. So one is that the equation here has a non-zero solution for V, and one of the others is that the determinant must be 0. Okay, so the determinant of A minus lambda I must be 0. Just so that you know, the determinant of a matrix is actually equal to the product of its eigenvalues. What you're seeing up here is that we've got this modified matrix and we're saying that it has an eigenvalue of 0. Okay, let me put this aside and let's write out A minus lambda I for the 2 by 2 real case. So that will be A, B, C, D minus lambda 0, 0, lambda, like that. Now let's do element-wise subtraction. And there you go. The determinant of a 2 by 2 matrix is easy to do. Remember that the determinant of a matrix of a 2 by 2 matrix is that you multiply there and add, and multiply there and subtract. So A minus lambda times D minus lambda minus B times C. If I FOIL all of this out, I'm going to get AD minus A lambda minus D lambda plus lambda squared minus BC. And if I regroup things and put all of the terms in a nice order, we get this. So first thing to notice is that if you plug in lambda equals 0, then you simply get determinant of A equals AD minus BC. So the solution here, or sorry, the coefficient here is in fact just the determinant of A. The other thing that you will see is that the trace of A is the sum going down the main diagonal. So notice trace of A appears here. So determinant of A minus lambda I actually has the form lambda squared minus tau lambda plus big delta, where big delta is AD minus BC and tau is A plus D, and this is the determinant of A and tau is the trace of A. The trace of A, incidentally, is the sum of its eigenvalues. So remember, the determinant is the product of the eigenvalues. The trace is the sum. And an easy way to see that in the case of 2 by 2 matrices is to factor a quadratic equation like this. So this has two solutions, lambda 1 and lambda 2. And if you expand this out, you'll get lambda squared minus lambda 1 lambda minus lambda 2 lambda plus lambda 1 lambda 2. And if I combine like terms, oops, I left out my variable there. If you factor it out and then say that I expect this equation to factor like this, then when you match these things up, the equations have to be true as an identity if this is going to be the factored form of this. That means that the coefficients have to line up. So indeed, tau is lambda 1 plus lambda 2, and delta is lambda 1 times lambda 2. And as I said, that this is a pattern that continues for square matrices of all sizes. Okay, so what does that tell us about this diagram? Well, if the origin is a saddle, well, that means that we've got one negative eigenvalue and one positive eigenvalue. So the determinant is something negative. It's a product of a positive number and a negative number, so the determinant must itself be negative. And if you look on this diagram, this part where you see it says saddle points, that's where the determinant of the matrix is negative. And that corresponds to having an eigenvalue of each sign. Okay, if the origin is a stable node, that means that both eigenvalues are negative. They're real numbers and they're negative. So the determinant is positive. And lambda 1 plus lambda 2 is a negative number. So the trace is negative. But this requires that lambda 1 and lambda 2 be real. We need real numbers for lambda 1 and lambda 2. They satisfy a quadratic equation, and sometimes quadratic equations have complex roots. So how do you tell whether this has real solutions or not? Well, you use the quadratic formula. So here we go. Lambda equals negative of minus tau plus or minus the square root of minus tau squared minus 4 times a times c delta all over 2. And when you simplify this, we'll get tau plus or minus the square root of tau squared minus 4 delta over 2. And so those are the solutions. Those are the eigenvalues expressed in terms of the trace and determinant. Well, in order for these to be real, so lambda, I'll call these, let me give these names, lambda plus and minus, are real if tau minus 4 delta is a positive number, so that we get a positive square root right there. Okay, so going back to here, if the origin is a stable node, that means that the determinant is positive, the trace is negative, and tau squared minus 4 delta is greater than 0, so we get positive numbers out of the quadratic formula in the first place. Okay, well, in the tau delta plane, well, I guess I should call it the delta tau plane, if I sketch in the line tau squared equals 4 delta, which I get by moving this over, that gives me, so that gives me, let me rewrite it as delta equals 1/4 tau squared. That will be a parabola like this. So you have to think of the delta as being a dependent variable and the tau as being independent, and sketching this line, sketching this curve. Okay. Up in this part, delta is greater than 1/4 tau squared. So in this part, the determinant is negative. Sorry, in this part, the delta, sorry, tau squared minus 4 delta is the discriminant. I forgot to give you that name. This is called the discriminant of the polynomial. Discriminants can be generalized to polynomials of any degree, but this is the one for a quadratic. So this line here, this parabola is where the discriminant is 0, and within the concavity of the parabola, the discriminant is negative. Let me clean this up a little bit. This is delta equals 1/4 tau squared. Outside the parabola, the discriminant is positive. which means that the region that we're interested in here, so the determinant is positive and the trace is negative and the discriminant is positive, that means that we have to be on the outside of the parabola and on the right half of the plane where delta is positive, and in the bottom half of the plane, which means that let me write this in a different color. Stable nodes are here. Okay, let's continue. If the origin is an unstable node, okay, that means let me draw it like this. Lambda 1 is less than 0, and there's a lambda 2. So again, delta is positive because it's a product of two positive numbers, lambda 1 and lambda 2. And lambda 1 plus lambda 2 is greater than 0. So tau is also positive. And again, we need to get real numbers out of the quadratic formula, so tau squared minus 4 delta must be greater than 0. So that means that, let me kind of move this around. Okay, I give up. In case it's not obvious, I'm having some trouble with the stylus. So let me redraw the plane over here. So there's delta and tau. Here's the parabola where the discriminant is 0. The discriminant is positive outside the parabola, so that puts us, puts us not in here. Delta positive puts us on the right half of the plane. Tau positive puts us in the top half of the plane. So the unstable nodes are here. Okay, next, if the origin is a stable spiral, okay, that means that tau squared minus 4 delta must be negative. That way we get complex numbers out of the quadratic formula. So lambda 1 and 2 are equal to alpha plus or minus I beta. Stable depends on the real part of the eigenvalues. So just to remind you of this, the real form of these solutions is an e to the at part times an oscillatory part. So if e to the alpha t times an oscillatory part. If alpha is negative, then this term will shrink and we'll have a stable spiral. So, and alpha is less than 0. Now at this point, remember that the trace, tau, is the sum of the eigenvalues. that's going to be 2 alpha in the case of a pair of complex conjugates. So that's telling us that tau is less than 0. Okay, so let me come back here and draw my delta tau plane and put in the discriminant 0 line. We are now going to be in here somewhere, and the trace is less than 0. So that means that there are stable spirals here. Now, it may be not immediately obvious why the determinant is necessarily positive. Well, lambda 1 times lambda 2, in this case, is going to be alpha plus I beta for lambda 1, but then alpha minus I beta because the other eigenvalue is the conjugate of the first. And if you FOIL all of this out, you get alpha squared plus beta squared, which is always positive. So the determinant will always be positive for a spiral. It's the trace that tells you whether it's a stable spiral or an unstable spiral. And if the origin is an unstable spiral, well, that means tau squared minus 4 delta is negative, so we get complex numbers out of the quadratic formula. Again, lambda 1 and 2 are equal to alpha plus or minus I beta for real numbers alpha and beta. And this time alpha is greater than 0 because the exponential part has to grow for the origin to be an unstable spiral. Again, tau ends up being 2 alpha, and that's positive, which means that when I draw the diagram, I need to put unstable spirals inside the parabola and with positive trace. So unstable spirals go here. There are a few other cases that you have to look at. These are the very borderline cases. So in the case of tau squared minus 4 delta equals 0, there are 2 possibilities. I've showed you stars. There's another possibility called degenerate nodes. And as to which you get, that depends on eigenvectors. So that depends on the eigenvectors. So tau and delta don't pull any information from the eigenvectors, so it's not possible to determine just from the trace and determinant which of these is the case. So I will talk about those in another video. Now, what about the case of centers? Case of a center. Okay, in this case, that means that the discriminant came out negative. So tau squared minus 4 delta is less than 0, so we get complex numbers out of the out of the quadratic formula. We get lambda 1 and 2 are alpha plus or minus I beta. But for a center, remember, alpha comes out to be exactly 0. Oops. Well, then tau still works out to be 2 alpha. It's just the sum of the two eigenvectors, sorry, two eigenvalues. So that has to be 0 because lambda 1 and 2 are just 0 plus or minus I beta. So that means that on this diagram, oh, let's see, what color haven't I used? How about purple? The discriminant has to be negative, which means that centers are inside the parabola. And furthermore, the trace is 0. So centers occur only on that line. And that should make some sense because that's the line that separates stable spirals from unstable spirals. And I can show you in the numerics. Let me go back to my numerical methods here, that this is with alpha equals 0. The real part of the eigenvalues is 0. If I go a notch above, the dynamics show an unstable spiral. Let me go back to 0 and let me go down a notch. If I go down a notch, it's maybe a little hard to tell, but the dynamics are showing a stable spiral. So right on the border between a stable spiral and an unstable spiral should be this marginally stable center case. So that is what's happening right here. Now, if the determinant delta is actually equal to 0, that means that one of the eigenvalues is equal to 0. And in this case, a lot of weird things can happen. So that means that AV is equal to 0. So let me call it AV1 equals to 0. That means that A is in fact singular, and you have this AV1 equals 0. And if you do e to the TA times V1, well, when you write this out, you're going to get I plus TA plus 1/2 t squared a squared plus 1 over 3 factorial t cubed a cubed times V1. Since all of these have a factor of a except for the first term, you're going to get just V1 out of it. And furthermore, if you now take the derivative, you'll get e to the TA times a times V1, which ends up being just a times V1, which ends up being 0. So what that means is that any non-zero V1 for which a V1 equals 0 is another fixed point. The origin is always a fixed point of these linear systems, and that's what we've been focusing on. The wrinkle here is that now we've got something called non-isolated fixed points. And to show you some of the numerics, let me go back up here to my previous interactive diagram here, and I'm going to set lambda 1 to be exactly equal to 0. Actually, let me just type it in. 0. And if I move this to be, well, it's hard to do. I don't have a way to type in this location. But you can see everything, it's clearer by the arrows as well. There are little dots here because the vector field is 0 along the horizontal axis, along this axis parallel to V1. So that's showing you that there's a whole line of fixed points in addition to the fixed point at the origin. So now let me show you the diagram and all of the parts of it all put together. Remember that saddles happen when there are two real eigenvalues, one positive and one negative, in which case the determinant is negative because it's their product. So that happens over here where the determinant is negative. When the determinant is exactly 0, that's this vertical axis, and that's where you get these non-isolated fixed points. On the right half of the plane is where you get spirals and nodes and centers and a few other things. The centers happen where the trace is 0. That's where you get a pair of pure imaginary eigenvalues. And if you work it out, the determinant comes out positive right there. In this quadrant, tau is negative. That indicates that we're getting stability. And the distinction between a stable node and a stable spiral happens along the curve where the discriminant is 0. Likewise, in this quadrant, the origin is unstable and it's either a node or a spiral, again depending on which side of the 0 discriminant curve you're on. Finally, there are these odd cases of stars and degenerate nodes. Those happen when the discriminant is exactly 0. That's when the two eigenvalues are real and equal. And again, distinguishing stars from degenerate nodes requires knowing something about the eigenvectors, and so there's nothing on just this diagram that can tell you how to make that distinction.